Next, we'll move on to the goodness of fit test, which will apply when we wish to determine whether a set of data may be viewed as a random sample from a population with a given distribution. In particular, this test involves comparing observed values with expected values, and we'll compute those expected values under the assumption that the data fits this given distribution. We'll consider two different scenarios that we might encounter when performing this goodness of fit test. In particular, the first will involve the situation when the category probabilities are completely specified. So what that means is for our random variable, the values that the random variable takes on will fall under a specific list of categories, say K categories, and that the value of the random variable will land in a particular category with a specified probability. So, for example, we might say that when we're interested in category number 1, the probability that's associated with category number 1 will be P1 naught. Similarly, the probability associated with category 2 will be P2 naught, and P3 naught for category 3, and so on down to the last category, K. The probability associated with that category will be PK naught. Again, we will be looking at some data where we have observed frequencies for each category. Then we'll compute expected values for each category by taking the total number of observations and multiplying it by the specific probability associated with that category. In other words, the expected value for category 1 would be the total number of observations, n, times the probability for that category, P1 naught, and so on down through category K. As such, our hypotheses will be defined as follows. The null hypothesis will say that the probability for the first category will equal P1 naught, the probability for the second category will equal P2 naught, and so on down to PK. The probability for that category for the kth category will be PK naught. In other words, we're saying that the data fits the given distribution given by these specific probabilities. And the alternative hypothesis would say that for one of those categories between I and K, the probability is not equal to that specified probability Pi naught. In other words, the data will not fit the given distribution if just one of those probability statements fails to be true. Our test statistic here is again going to be a sum. Now remember, Ni here corresponds to an observed frequency. NPI naught corresponds to an expected frequency, so we're looking at the difference between the observed and the expected frequency in a given cell, and we're squaring it and then again dividing by the expected frequency and summing over all of the categories for our random variable. In other words, we could say then that if we take the observed value for the ith category minus the expected value for the ith category, square that, then divide by the expected value for that category, and then sum up over all of the categories, we'll get our test statistic. So this is perhaps a simpler way of writing it, but just to help keep it fresh in your mind, observed minus expected squared divided by expected, and then sum over all categories. You'll see that this is very similar, if not identical in nature, to the way that we defined our test statistic for the independence test. Now here, our degrees of freedom will equal 1 less than the number of categories that our random variable will take on. And the associated rejection region will be a right-tailed region where we chop off an area equal to alpha in the right tail. And so we're looking for a chi-square score with the area to the right equal to alpha and k minus 1 degrees of freedom for that distribution. And that tells us our critical value for our rejection region. So let's consider an example. Mendelian theory states that the number of a certain type of P falling into the classifications round and yellow, wrinkled in yellow, round in green, and wrinkled in green should be in the ratio 9 to 3 to 3 to 1. In other words, the probability that a certain type of P is both round and yellow should be 9 over 16. The probability that a certain type of P is both wrinkled in yellow should be 3 over 16. The probability that it's round in green, 3 over 16, and the probability that it's wrinkled in green would be 1 over 16. Let's suppose that we have a random sample of 100 such P's, and we ended up with 56 round in yellow, 19 wrinkled in yellow, 17 round and green, and 8 wrinkled and green peas. And we're interested in determining if the data for our random sample is consistent with the Mendelian model. And so we're going to test at the 5% level of significance. So we'll put our information into a table. You can see the 4 columns of the table correspond to the different categories of P that we could have. So we have 4 columns for our 4 categories. And then the top row underneath each header for the column corresponds to the specified probabilities for each category. Probability that we get a round yellow pea should be 9/16, probability wrinkled in yellow 3/16, and so on. And then I've listed the observed values in the corresponding categories. So then the next thing that we want to do is compute expected values. So remember, our expected value should be the number of observations times the associated probability for a given category. So if we want the expected value then that we have a round yellow pea, then we're going to take the 100 peas in our sample and multiply by 9/16. If we do that, we get 56.25. So that number goes in the expected slot for round and yellow peas. If we want the expected value for the wrinkled yellow pea, we're going to take our 100 peas in our sample and multiply by the associated probability of 3/16. If we do that, we get 18.75. And we'll put that into the appropriate cell in the table. And we can fill out the table, those last 2 slots, in a similar fashion. Now we've added in all expected values for our 4 categories, and the next thing we will do is define our null and alternative hypotheses. In particular, the null hypothesis will state that the probability that we get a round yellow pea is 9/16, probability that we get wrinkled yellow pea is 3/16, the probability that we get a round green pea is 3/16, and that the probability that we get a wrinkled green pea is 1/16. In other words, our hypothesis saying is that the data fits the given distribution described by the Mendelian theory. The alternative hypothesis would say that the data do not fit the given distribution, and in order to argue that's the case, it would be sufficient if just one of those probability statements didn't hold true. Now on to computing the test statistic. Remember, we're going to take our observed value, subtract the corresponding expected value, square that, then divide by the corresponding expected value, and we'll add up over all categories. So I've done that here. Remember, we had 56 round yellow peas minus 56.25 expected round yellow peas. We square that and divide by the 56.25. We do that for all 4 categories, and our test statistic is 0.657. Now, our rejection region, remember, is determined by a chi-square distribution where the degrees of freedom is 1 less than the number of categories, so 3. And our alpha value is 0.05, so we're going to find a critical value where we chop off an area in the right tail of 0.05 with 3 degrees of freedom. If we look that up on our chi-square table, we get 7.815. And since our test statistic is not in the rejection region, we fail to reject the null hypothesis, and therefore there's insufficient evidence to suggest the data do not fit the model. In other words, we can say that we are convinced at this time that the data is consistent with the Mendelian theory.